Hello everyone, welcome back to my channel. I am Bhagyashree, studying BE second year at Sri Venkateshwara College of Engineering, Bangalore. Now I am here with a new topic, homogeneous recurrence relation with constant coefficients. Introduction to homogeneous recurrence relation with constant coefficients. Homogeneous recurrence relation with constant coefficients are mathematical equations that describe a sequence in which each term is a linear combination of previous terms. This relation play a crucial role in various fields of mathematics, including combinatorics, algebra, and computer science. Understanding and solving these equations are fundamental in analyzing the behavior and patterns of sequence. Of homogeneous recurrence relation. Homogeneous recurrence relation is the equation of the form of A of n, C of 1A of n minus 1 plus C of 2A of n minus 2 plus idos plus C of Ka of n minus k, where C1, C2 are idos, C of k are constants. The terms on the right-hand side of the equation represent linear combinations of previous terms in the sequence. The subscript denotes the position of the term in the sequence. Characteristics of constant coefficients in homogeneous recurrence relation. Constant coefficients in homogeneous recurrence relation do not depend on the position of the terms in the sequence. These coefficients remain fixed throughout the sequence and are essential in determining the behavior and solution of the equation. The values of the constants influence the nature of the solutions, such as whether they are exponential, polynomial, or a combination of both. The solution of the homogeneous recurrence relation with the constant coefficient often involve finding the roots of the characteristics equation associated with the relation. The characteristics equation is obtained by substituting a of n r to the power of n into the recurrence relation and simplifying to find the roots of r that satisfy the equation. The general form of the solution is a linear combination of terms involving the roots of the characteristics equation raised to the power of the position in the sequence. Example of solving homogeneous recurrence relation. Consider a recurrence relation of a of n equal to 2a of n minus 1 minus a of n minus 2 with initial condition a of 0 equal to 1, a of 1 equal to 2. The characteristics equation is r square equal to 2r minus 1, which simplifies to r minus 1 power to the 2 equal to 0 with the double root of r equal to 1. The general solution is a of n equal to c of 1 plus c of 2n, c dot 1 power n equal to c of n plus c of 2n, where c of n and c of 2 are determined by the initial conditions. Stability of solution in homogeneous recurrence relation. The stability of solution in homogeneous recurrence relation is determined by the roots of the characteristics equation. If all roots have magnitudes less than 1, the solution tends to converge to a constant value as n approaches infinity, indicating stability. Unstable solution result from roots with magnitudes greater than 1, leading to exponential growth or decay in the sequence. Recurrence relation with multiple roots. In some cases, the characteristics equation of a homogeneous recurrence relation may have multiple roots with multiplicity greater than 1. Multiple roots introduce additional terms in the general solution, representing the linearly independent sequence associated with each root. The presence of multiple roots can lead to more complex solution expressions, but can still be determined using the initial conditions. Homogeneous recurrent relation with complex roots. If the roots of the characteristic equation are complex numbers, the solution of the recurrence relation involve complex exponential functions. Complex roots come in conjugate pairs, leading to oscillatory behavior in the sequence. The real and imaginary parts of the complex roots contribute to the overall solution, reflecting both exponential growth, decay, and periodic oscillations. Non-homogeneous recurrence relations. While homogeneous recurrence relations focus on linear combinations of previous terms, non-homogeneous recurrence relations include additional forcing terms on the right-hand side of the equation. Non-homogeneous relations require a particular solution to account for the forcing terms, in addition to the general solution of the associated homogeneous relation. Techniques such as the method of undetermined coefficients or variation of the parameters are used to solve non-homogeneous recurrence relations. Advantages: analytical solvability, closed form solutions. Homogeneous recurrence relation with constant coefficients often allow for closed form solution which provide explicit formulas for terms in the sequence. This makes easier to analyze and understand the behavior of the sequence. Predictability. Once the characteristic equation is solved, the entire sequence can be determined using initial conditions, providing a clear and predictable formula for future terms. Simplicity and elegance. Mathematical elegance. The method used to solve these recurrence relation, such as finding roots of polynomials and using initial conditions, are straightforward and elegant. This simplicity is aesthetically pleasing and easier to understand and teach. Reduced complexity. Compared to non-homogeneous or variable coefficient recurrence relations, homogeneous relations with constant coefficients are less complex and more manageable. Disadvantages: analytical solvability, predictability. Once the characteristic equation is solved, the entire sequence can be determined from the initial conditions. This predictability allows for precise forecasting of future terms in the sequence, which is valuable in applications like financial modeling or algorithm analysis. Simplicity and elegance, mathematical elegance. The method of used to solve recurrence relation, such as finding the roots of the characteristic polynomial and using initial conditions, are straightforward and elegant. The simplicity of these methods makes them aesthetically pleasing and easier to understand and teach. Applications of homogeneous recurrence relation. Homogeneous recurrence relation with constant coefficients are prevalent in various mathematical and computational contexts. They are used to model and analyze sequences in fields such as cryptography, signal processing, and algorithm analysis. Understanding the behavior and solutions of these relations is essentially for optimizing algorithms, predicting patterns, and designing efficient systems. Summary of key points. Homogeneous recurrence relation with constant coefficients describes sequence as linear combinations of previous terms. Solution involve finding the roots of the characteristic equation and determining the general form based on initial conditions. Stability, multiple roots, complex roots impact the behavior and complexity of solutions in these relations. Conclusion. Homogeneous recurrence relation with constant coefficients are powerful tools in mathematical analysis and modeling. By understanding the principles and techniques for solving these equations, mathematicians and researchers can uncover patterns, predict trends, and optimize systems. Continual exploration of homogeneous recurrence relations, which contributes to advancements in various fields and depends our understanding of mathematical structure. Thank you for watching. Please like, share, and